And hello, here's Mr. C. This is a recording for Lab 305, Conservation of Energy, and I'll do this as a separate screencast so you can follow when you do the lab. We have the instructions here on the upslope of Mount Rainier, and on the top we have the answer key, so the lab report. I saw GA in there. Anyhow, so let's briefly look at the lab report. You're going to see a lot of points there. It's altogether 52 points, so it makes sense from a perspective that this really concludes mechanics. You know, we are at the end of it. We're going to use kinematics in here, graphing tables, so it's really important that you shine in this lab and get a lot of points and show me what you learned there. You see the rubrics on the side. If you don't know where to find them, ask me. You're going to put results there, and I'll walk you through it today. I want you to define key terms, the ones that I highlight currently, and then you're going to write your answers down here. You have another table here and two figures. And another block here, you're going to discuss how the velocity and the velocity squared relate to the height from which the ball was released. So we're going to have the familiar ramp with the ball rolling down. So there shouldn't be any problem with using that lab, and whether the relationship is linear or non-linear. And at the end, something from the current unit, you know, how is work, potential energy and kinetic energy related in these experiments. And I hope you find conservation of energy there, right? So give a good answer and follow please these rubrics on the side. So let's close that, and we'll go quickly to the instructions here. It's always good to look at the end in mind. Here's our link to the virtual lab, and we're gonna have to work on this table in the first part, and a very similar looking table on the second part, and then we're gonna make two graphs. So let's start with the top here. I'm gonna open up that lab right now because it's more intuitive that way. So here's our lab. You can go to the tutorial and we'll begin the lab. The lab is modified, one of the more strongly modified labs I've modified because of some mistakes or something doesn't come out right. Really doesn't help us much in showing conservation of energy. The first thing is we're going to measure the weight of this ball here. So I'm going to put the dish on there on the scale. These are grams, so 9.9 grams. Your number will be different, 9.9, and we have 260. So I'm going to write this down, 261.45 and 9.9 grams. And we need to convert those into kilograms. That's all we need on this side of the workbench. Going to start moving things to the left because this is where we're going to do work. I'll show you one time why I have a little headache with the lab. We're going to do this on one set, but you don't have to use the timers for that reason that I'll show you in a second. Okay. The reason why we have these timers and the gate is that we are measuring the final velocity. To get the kinetic energy at the end, we need the final velocity, and that's what we're shooting for here. So we place the ball behind that gate, and we're going to need that ruler here. These are all in centimeters, right? So this is the setup, and we're going to study the height here. So this time this ruler, the long ruler here, is important. We need to know how high the ball is, and I'm going to zoom in for that purpose one time here. You want to look at that blue, the center of the blue triangle, not the tip. On the tip I would read now 7 centimeters. I would say in the middle about 7.5 centimeters. I know it's not exactly at the center of the ball, but it happens to be working out, the numbers work out better if we use it. So there are a lot of things in this model that are not perfect. So use the middle of the blue triangle. So here I would read 7.5 centimeters off, and it's currently at the 85 centimeter position on the ramp. Let's briefly look into the lab. I'm going to select the table because that's what we're going to start filling in a second. So we determined the mass of the ball, we record it in the table, we write it right here in a second, and then we set the angle at 5 degrees and place the starting gate somewhere between the 80 and the 100 centimeter line. And then we measure the vertical height using the metric ruler. Okay, let's do that for now. And we measured the 7.5 centimeters, so I'm gonna go over and cut and paste this into an Excel sheet. And I hope I'm desktop sharing, so you should see this all beautifully. So this here, this value should be equals to 261.45 minus 9.9 grams over 1000. And I hope you know why I put over 1000, because this needs to be kilograms, right? And the angle there, the angle of incline is 5 degrees, and we measured a height of 7.5 centimeters. You can either write 7.5 or 0.075, because this needs to be in meters, you see up here. And the length of the incline at that point was 0.85 meters. Okay, that's what the location was where we're at. So now the original lab asked us to use the photo gates and to calculate the final velocity, to experimentally determine the final velocity. I'll do it one time here, but we're going to use a calculation. We're going to use kinematics, and I'll show you the equations down there. Okay, so then we change the angle of the incline, but keep the height of the ball constant. So that's a bit tricky. So we need to change the angle. We started out at 5. We're going to go maybe to 7, 9, 11 or something like this. And we need to find the position where we're going to place the starting gate. Okay, so there are two ways of doing this. One is the mathematical way to calculate it, but let me just finish this one here. We need to find the acceleration that is basically leveraged by that ramp, and the equation I have in the report here, the acceleration J is g times sine of the theta of the angle. So we're harvesting a certain portion of the acceleration to the gravity on the ramp, and it's just a fraction of g times the sine theta. So let me do that in here. It brings us to our first caution or alarm sign, equals, so I do 9.8 times. What I mean with that is we need to put in the sine, right, of theta, and we could just link it to the 5 degrees here, but that would be wrong, because the sine needs radians, so we need to change this into degrees. 3 degrees off, and we're going to go over here. The degrees function changes that number over into radians, and that's the wrong one, so we need the radians function here. Exactly the opposite. Radians converts degrees to radians, so we need the radians to go over here. That was tricked. Okay, so now we have the acceleration is 0.85 meters per second square. The final velocity we can also get from kinematics, and I have your equation here too. So B final is the square root of 2 times 8 times the distance. Let's calculate that here. So here work equals 2 times the square root SQ RT of 2 times the acceleration, now we calculated, times the distance, 0.85. And that's the final velocity. And again, way too many sig figs. And it's about 1.2 meters per second. Okay. Now, and we can calculate all the rest. I just want to get to this point of the 1.2. If we were to do this experiment here, and we might actually get close. That's always the dilemma when you show something. So we're at 85. We have the timer set at 0. If we release the ball now, we did all the measurements, so just release it, and it's rolling down here for half a meter. Reset 0.793. Oh, I was faster resetting it. 0.793. So we had a time of 0.793 over 0.5 meters, right? Or 0.5 meters per second. So 0.5 meters over 0.793 seconds. So it would be 0.63. Yeah, it would be 0.63 meters per second, which is way off. Okay, and so this whole thing won't work, and so I'd rather go with the calculated value of the final velocity than with these measured ones and have all kinds of errors, not demonstrating our primary goal is the work and energy is equivalent, right? Based on that number now we're going to calculate the parallel component of the weight. And the parallel component of the weight, if you were to draw a free body diagram, we have done that in the past, is again just the sine theta component. So it's m mass times acceleration. Well, an acceleration is g sine theta. So we just need to multiply m with the acceleration that we just got, right? The mass times the acceleration value. So let's go back here. This is the mass up here, and I'll put the mass in dollar signs because I don't want to change it when I drag it down, times the acceleration. So this is 0.21 Newton. Okay, and work is force times distance, right? Is force times the 0.85. So this is 0.18 joule. Potential energy is mgh equals the mass times 9.8 times the height, and the height is 0.075 meters. So I want to put the dollar signs here again, and so it's close, right? The potential energy is equal to the work. Look at that, pretty good. And now we need to calculate the kinetic energy. 1/2 mv squared equals 0.5 times the mass, and I'm gonna dollarize that again so it doesn't change when I drag the equation down, times the velocity to the power 2, 0.18. Look at that. And that's how I think what the designers were looking for, right? Work basically, well, the potential energy, where is the positional energy, is where the ball is stationed, goes into work when it rolls down and becomes kinetic energy. And you're going to do the other examples, then, then you're going to change the degrees, maybe to 7, maybe to 9 and 11. The challenge there is now to keep the height constant, right? So we need to move the position of the starting gate. So we want to keep it at 7.5, and I'm going to bring up that lab again. So if we change it, we're not using the timer here. If we change the gate here, the ramp here, I go 2 slots up, then to keep it at 7.5, I need to move the starting gate. I need to not open it. I need to move it. I need to grab it and move it down. And so I think 65 might do it. I'm going to check it out. Again, we're going to measure at the triangle. And it looks about right. We can zoom in there. Yeah, it's a bit higher. Maybe 60. It's more 60, right? So the middle of the triangle, not the tip and not the base. So maybe 60 is a better value, right? 60, and then you actually don't need to do anything, right? We're not measuring anything, so you can go right there and say, hey, I'm gonna measure 0.075 at a distance of 0.60, and now if you did everything right, you're just gonna drag that whole equation, selected it down 1 slot. Okay, so we have this acceleration, we have a slightly different velocity, probably if we add the distances, parallel force, here the work. We need to check something here. Something is not right probably, and I'm glad these things happen because you have the same issue always. Precedence, force times distance. I'm gonna uncheck this one. I want to check. I have this one right. length. I have this one right. Something is not doing it right. MGH, we have this one. Why is work twice as much? Force parallel component needs to be higher because we're now at 7 degrees, so we're harvesting more acceleration. This is higher potential energy. What about this one? Move arrows. I'm holding on. Let me see. And I think I found my mistake here. This was in this equation already, and that I used the acceleration where work is force times distance. I should have used C4 for that one, but I fixed that, and now if I drag it down, yeah, it works beautifully. Okay, and you're gonna do the rest. You can of course do a little trick to find out this position here. You could use trigonometry and then place it, come from that side, but I think you get the point in the first part of the lab. Let's go to the second part here. Okay, there was no graphing, you just bring the table back into the lab. So then the second part, we choose an angle, and we're gonna change the, so when the angle is fixed, we're gonna write the angle theta here, and enter it in the first column. So this will be all the same value. We then place the ball at different heights. We'd have to then place the ball at different heights and measure where it is, right? So in order to place it at 004 or 4 centimeters, it will be far to the right, and if you point 160, it will be far to the left. Let me just bring over the table to an Excel sheet. So workbook here. I make a new sheet here. So we're gonna have the mass of the ball the same. Well, I could be just doing an equal sign and go back here. It's the same ball, right? The angle between, what did I say, 10 and 12, 10 and 14, so let's pick the angle theta. I'm gonna put maybe 13 degrees for now, and I keep that constant, so that's all constant. We need to find out the length, basically, where the height is 0.04. So we go back to the lab, and if you haven't realized it, you can do this lab without the lab. It's purely a trigonometry exercise, but it kind of gives you confidence what you're doing, right? So we want to set the lever to, this is 10, 11, 12, 13, and I want to set it at 0.04 height. So I know if I go here, say at the 20, and I think it's pretty close to that. Let me zoom in here. Go down here. So 0.04, and look at that. It's pretty much where my index finger is here, over here, pretty close to that. So at 20 is the 0.04. I can go back here and put here 0.20, meaning 20 centimeters, right? And maybe add one sig fig here, right? And then we need to bite 0.08 all the way to 0.16. Let's go to the last one here just for kicks, the 0.16, 16 centimeters. So grab, I'm staying zoomed in. I don't know whether that's a good idea. Go to the left. Okay, if I drop that here, oh, I'm pretty close, I think. So maybe this is 16 and a half. If I bring that thing down to 70, and we only can go in increments of 5, it's 15 and a half. So it's somehow between 70 and 75. Well, you know, you can do 72. We're not doing the actual experiment, so might as well take advantage of that and say, hey, down here it's 0.72. Okay. Now the neat thing about this is you're done with the work. If you did it over here, the equations are the same. So I copy this row over to the other side. It's always worth checking, right? Does this make sense? Are we using the right formulas? I like to see the precedence and the dependence. So 2.2 makes sense. So we're more steep, we're harvesting more of the acceleration due to gravity. Then the equation here makes sense. 2 times d4. Again, I go back to formulas. d4, that length. So I think everything is alright here. That means I can take this equation, go down here, and look how well it's conserved. That's the table that you're gonna bring back with all the other values inserted here too. And I hope you're seeing the benefit of using these equations, right? Go back to the lab now. And then we need to make two graphs, velocity versus height. So velocity is on the y-axis and height is on the x-axis. So I'll show, this is velocity is on the y-axis. So we have final velocity. So this goes on the y, this goes on the x, and then one time we need to show velocity square. So we probably need to make a helper column to make that graph, right? So you go back to Excel and you say equals, here's the velocity, and we square that. And of course we bring it down. You don't need to show me the values, the graph needs to be right. So so we have 1 times velocity here, and then I'm holding down the control key versus height, and this is one. I think I can even grab the titles here and go to insert charts, scatter. You get something like this, and it needs to be 0.9, yep, 2.2. Just fix the titles and whatnot, right? And look at the shape of the graph. Is it linear? You expect it to be linear, you know, and when you then graph velocity square, maybe we should write it up here, vf to the power 2, right? And it should be an underscore and the lowercase everything. I don't know, why do I have caps on? F squared, right? You're holding down this key here. I think by now you're good in graphing. Sometimes I see you're forgetting to add the add something. Let's see if that works, because the right one is not combined up there. Insert chart. No, it didn't. So, and we know probably why, because these columns, they are not combined, so you need to merge them. Maybe now it works. So if I have this on X, this on Y, insert charts, boom, yeah. And then you draw a trend line through that. Okay. Yeah, I think the values look about right. X doesn't look right. This looks like indices. Something is not right. You might have to. What I suggest is, if you have trouble with graphing, this has something to do with these combined cells here. So it's better to then just make separate data. Move just the data out, like down here maybe. Values, and then graph it from here. Here's height, and here was velocity, and here was velocity squared. So that will work. Height, I just show the velocity squared. Insert charts. Yeah, here's the right axis. You see there are discrete values on the x-axis. The other one used just numbers. I didn't like that one. Okay. All right. So you bring those two graphs over and you talk about it. Hopefully you see a shape difference, and hopefully you can explain that to me. Has to do with, you know, energy conservation, basically the relationship between both things. One, the height represents potential energy, right, and velocity square represents kinetic energy. So that's about it on this lab. So it's an old one, like kinematics included too, and please do a good job. If you need key terms, you can find them in the student resources, and there's one tab that says keywords. It takes a while to refresh, but that's where you find definitions, and I'm looking forward to seeing your work and getting questions. Thank you for watching.